inverted, and you want to take a little atom of mud and you put it in this hole in such a way so that the total transport distance of taking this particle of mud and putting into hole is smallest. The work that you have to do is minimum. Also, I'm cheating a bit. Monge's problem actually did not have this 2 there. It was actually just about the norm. But for reasons that will become very clear, 2 is very good. 2 is always a very good number. And so we'll always use 2, although this was not the original problem of Monge. But anyway, this is what Monge's problem is. Among all maps from RD to RD that push forwards P to Q, minimize this expectation. The expected distance between Tx and X. Clear? Again, please do ask me questions. Correct. So very good question, because I'm going to change this in the next slide. But exactly as you are saying, so X is my atom. So there's an entire column of atoms here. The entire thing will go to T of X. That's correct. Exactly as Apurva alluded here, there is a fundamental difficulty here. And this difficulty can be realized in many, many ways. One is exactly, I don't know whether such a T exists that will actually solve my problem. This problem is not convex in T, so it's a very ill-posed problem. These are all related to this fact that if I take this whole column at X, Monge is telling me I must move the entire column to that of Y, and that's a very serious restriction. And I don't want to do it. It will be much nicer if I'm allowed to take this column and then break it into pieces and then move the different pieces to different locations. How do I mathematically frame this? This is the idea of couplings. So what is an idea of couplings? So suppose my mu and nu are probability measures. A coupling is any joint distribution with marginals mu and nu. People use the word coupling for many, many different contexts. This is the one that is important for us. A joint distribution of marginals mu and nu is a coupling of mu and nu. So this is my set of couplings, which I've drawn a picture of one coupling here. So if my mu and nu are one-dimensional, my coupling is a two-dimensional probability measure. Now, how do I know that the set of couplings is non-empty? There's always an obvious element in it, which is a product measure. If you take mu cross nu, the product measure, then that's a joint distribution with mu and nu as marginals. So this is always non-negative. And this is also a nice convex set of probability measures. If you take two measures with marginals mu and nu, and if you take a mixture of the two, then of course the resulting mixture will also have marginals mu and nu. Okay, so it's a nice convex set. Moreover, if there is such a T of X, when X is sampled from mu, T of X is nu, then X comma Tx is actually a coupling. It's a very special coupling, but this is a joint distribution of mu and nu. And now I realize that in the last slide I wrote P and Q, but P and Q are now mu and nu. Okay, so for a long, long time, nobody made any progress in Monge's problem. Until 1930s, late 1930s, and this is due to Leonid Kantorovich, the mathematical and economics genius from Soviet Russia, who what he did is that he said, okay, let's try to change Monge's problem. Let's try to remove this restriction that my entire column has to go from one place to another. And how would I change it? Well, look into all couplings of mu and nu. For every coupling, which is a joint distribution of mu and nu, let's look into the expected value of y minus x norm squared. Okay? Now, for a joint distribution, this makes sense. Now, among that set of joint distribution, this is a convex set of probability measures. Minimize this. Good. Why is this a simpler problem? It's a simpler problem because as a function of gamma, this is a linear function. The expectation of a particular function norm of y minus x squared with respect to gamma is an integral with respect to gamma, and therefore it's a linear function of the measure. So first of all, I'm optimizing a linear function. The set over which I'm optimizing, as I already said, is convex, and it's non-empty. So I'm minimizing a linear function over a non-empty convex set, And these problems, at least for the Euclidean space, is nice. They are the simplest class of problems for which we can do something. This is one of them, except it's infinite dimensional. But forgetting about that, it's nice. Right. So the solution will guarantee to exist. And this is because of this, from very, very weak abstract nonsense, you can show that the solution will exist. Rather weak arguments will tell you. Of course, when Kantorovich was doing this, this was the birth of linear programming, one of the great successes of modern mathematics. So what he was really doing over a discrete set of data. And I'll mention this, we were having this discussion in the afternoon. If you do this for a measure which is supported on a discrete set of points, this becomes what is called the classical matching problem. And this is really what Kantorovich was doing. And so you have a classical matching problem, and this problem then becomes what we call a linear programming problem. It's a linear function being minimized over some Euclidean convex domain, the linear programming problem. And this is how did you solve it, where you come up with these algorithms, like the great simplex algorithm. And you solve it, and this is really what, Kantorovich and Danzig and all these great people who have all worked on this, they have done this. So they have basically reduced the problem, which is this Monge-Kantorovich problem, for discretely supported distributions. But we're not interested in discretely supported distributions, and for very, very good reason, for one singular theorem, which makes continuum much more appealing than discrete, and why everybody, when they do the discrete problem, they want to take the dimension, go to infinity, and make things continue. What is this theorem? Well, you ask yourself, how does this optimal coupling look like here? And what does it have to do with the original Monge's problem, which was asking for this map that will take my mu to nu, which minimizes its expected, this distance square. The beautiful result is called Brennier's theorem. It was proved in the second half of the 1980s by Jan Brennier. And Jan proved this wonderful, wonderful theorem. I want to go over this theorem slightly. If there is one thing you should learn from this talk, is this theorem. Suppose my measure mu, one of the two measures, mu, has a density. Then there's a unique solution to the Monge-Kantorovich problem. What does that mean? Look at the Monge-Kantorovich problem. It is minimizing this expected value over the set of couplings of mu and nu. A unique solution means there is one coupling that achieves this minimum. Lo and behold, that coupling is a very solution which is the solution that Monge was asking for. There will exist some function, phi, which is convex. If you look into gradient of phi, now if phi is a convex function from Rd to R, gradient of phi is a function from Rd to Rd. Clear? There will exist some convex function such that the gradient of phi will push forward my mu to nu. First non-trivial statement. Given any mu and nu, if mu has a density, there will always exist a convex function such that if x is sampled from mu, then gradient of phi applied to x has distribution nu. First non-trivial statement. The second non-trivial statement is that this coupling, where you look into x sampled from mu and gradient of phi of x, which this marginal now becomes nu, this must be the unique solution of the Monge-Kantorovich problem. So the Monge-Kantorovich problem admits a unique solution. The unique solution is of the solution that Brennier's was asking for, a function that push forwards mu to nu. That function is very special. It must be of the gradient of a convex function, and such a convex function will always exist. Clear? Grad phi is unique. Grad phi is unique. The problem has a unique solution. If I take a normal distribution, let's say a multivariate standard normal, and take any of your favorite other distribution, I don't know, I mean, some kind of exponential, some kind of heavy tail, giving my regards to my friend. Whatever this distribution is, as long as they have finite second moment, then there will exist some convex function. So that you plug in your standard normal, and gradient of phi applied to standard normal will give you that distribution. And this coupling is a unique coupling that will minimize the Monge-Kantorovich problem, to minimize the expectation of this y minus x squared. Wonderful, absolutely wonderful theorem. Yes. So for d equals to 1, if you have two one-dimensional distributions, so suppose my mu has CDF F, this is my CDF. For nu has CDF G. Then how do I get a map from mu to nu? Well, the answer is obviously G inverse compose f of x. This is my standard probabilist coupling. If x is from mu, then f of x is uniform, and then G inverse compose f is going to give me nu. You see what is being used here. Here is where my density is being used so that I get something that this is actually uniform. And the other thing that you notice here, this function, why is this the gradient of a convex function? Well, everything is one dimension. So gradient of convex functions are all functions that are increasing. So all I need to just verify that this is an increasing function. That's because they are both increasing functions, and compositions of increasing function is increasing. Good. So Brennier's theorem is true, and this is my unique solution. All right, okay. Why is there so much interest in optimal transport in statistics, machine learning, AI, etc.? You wouldn't believe me. I once got called by Silicon Valley venture capitalists because they wanted to talk to me about optimal transport-based methods because there are so many people who are looking for funds, and they wanted to ask me, is this genuine or is this not? So there's, in the last 10 years, at least in the last 5 years, there's been an explosion of interest in optimal transport-based methods in applications. And why is this real? Well, yes, there are many, many reasons why optimal transport methods can do things that were previously not being able to be done. So for example, one thing that you would notice here, that a lot of statistics is based on Kullback-Leibler divergence. One of the problems with Kullback-Leibler divergence is that if your two distributions have disjoint support, then your Kullback-Leibler divergence gives infinity value, right? So here I have taken uniform 2 to 3 and uniform 0 to 1. These have disjoint support. Kullback-Leibler is infinity. On the other hand, optimal transport-based methods is Wasserstein 2 distance between these two distributions. They're still finite. In fact, this is actually pretty easy to say what is uniform 0, 1 to uniform 2, 3. What is the map that will take uniform 0, 1 to uniform 2, 3? Well, you generate a number from uniform 0, 1, add 2. So what is the distance that you're making? 2. That's always finite. Good. So this kind of things actually is very convenient. So one particular example I'll give is manifold learning, where you assume that your actual data, your actual models are supported on a lower dimensional manifold, but you're observing data which has some noise in it. So people use this frequently. Another area where people use out of optimal transport is regression with uncoupled data. And this actually needs some explanation. So typically when we think of regression problems, you have paired data, right? Xi, yi, these are pairs, and you want to do regression between X and Y. Sometimes, an example being single cell genomics, where you get a sequence of X, you get a sequence of Ys, but you actually don't know which Xi comes with which Yi. There, the link is broken. You have some internal mechanism which tells you which is more likely to come from which one, but you don't know exactly which ones comes with one, and you would still like to do regression. And that's the reason when you do with optimal transport. In single cell genomics, what happens is that you're tracking the development of cells over time, but every time you open up a cell, it dies. And so you never have actually a time series. What you have is snapshots in time of different data sets of different cells, which are somehow linked together because they are given by the same biological mechanism. Optimal transport is the only known way, at least people use these things. As I also mentioned, that optimal transport are matching problems. They're basically matching problems in continuums. A lot of economics, for example, deals with matching. And so they do in continuum simply because they want to take advantage of Brennier's theorem. If you do matching on data, there is no Brennier's theorem. If you do matching in continuum, suddenly it tells you that the optimal solution must be gradient of a convex function, and that immediately reduces your search domain of what kind of optimal maps you're looking for. And that's one of the things that people use very often. Computer vision and graphics. So what do people do in computer vision? Optimal transport. So suppose you have like several images of the same object. Taj Mahal, people take millions and millions of photographs, and you have various images of the same object, Taj Mahal. If you want to do a composite image of this, you want to somehow average over images. Now, if you want to have an image like this, which looks like a normal curve, and if you take another image, which also looks like a normal curve, except shifted, and if you just take if you just want to take average in the usual way, you would get a curve like this. This does not preserve shape. So what I'm taking a mixture of two normal densities will give you a bimodal distribution. But there is a way in optimal transport you can do this, where if you take the average of this, you get this shape, which is basically the two shapes aligned together. And this sort of feature is a feature of optimal transport, very much used in computer vision and graphics. Sampling and image generation, this is very much coming up now from artificial intelligence. People want to do sampling, they don't want to do, there are other ways to sample now using optimal transport that does not use Markov chain Monte Carlo. They want to do image generations. By doing image generations, they want to run a diffusion model, but they don't want to run the diffusion model in a traditional way by sampling. They would run models using optimal transport-based methods. Each one of these are now areas of their own. I cannot cover them in our talk, but if you search by these keywords, image generation, optimal transport, you'll get number of hits. Essentially, the reason why people like optimal transport is because it kind of respects the underlying geometry and lifts them to the space of measures. And the reason is very obvious. If you take two delta masses, delta mass at x and delta mass at y is optimal distance, optimal transport between the measures is just a Euclidean distance of norm of y minus x. I'm happy to talk. Okay. Now, optimal transport is very good in all these things. There is one serious drawback, which is that it's computationally pretty bad. There are many reasons. However, as I said, people are using it all the time. So when they say they're using optimal transport, they're not actually using optimal transport. What they're using is a slightly regularized version of it, which is the main topic of my talk. Yeah. Right, so that's exactly my point is that you don't know, I know there is a fee, but I don't know how to compute it. So if I have data sets, I would like to actually compute that problem. And that computation, I'll come to a slide, is very bad, and it has a curse of dimensionality. And to get rid of this, you have to regularize the problem, which is what I'm going to talk about. Correct. So your sample complexity, yeah, it increases. So that's why optimal transport is geometrically rigid, statistically non-robust. Okay, so optimal transport, when it's actually used on data, it is a slightly change. And what the change is that it introduces an object called entropy. Well, obviously, all of you must have heard of what entropy, the word is. It's a measure, in this case, is a measure of degeneracy. Now, the differential Shannon entropy is a negative of optimal transport entropy. And so what I'm going to do here is that this is my definition of entropy. Entropy, if nu has density f, it's integral of fx log fx dx. If it doesn't have any density, then it's infinity. The way that you should remember it is that if you look into the entropy of normal 0 sigma squared, this is negative log sigma, which means as sigma is going to 0, your entropy is going to infinity. And when sigma is going to infinity, your entropy is going to negative infinity. This is a part which is important for us, that when sigma goes to 0, your entropy is becoming infinity. Entropy penalizes probability measures that are very degenerate. Okay. We'll also come to this. Kullback-Leibler relative entropy between two distributions P and R is given by this formula. There's P expectation of log dPdr. Now, various authors, for various reasons, have suggested that instead of looking into the Monge-Kantorovich problem, you do what is called the entropic regularization. So what is entropic regularization? Okay, look into this problem here. So mu and nu are given. Pi of mu and nu is a set of couplings. These are all the joint distributions of marginals mu and nu. Given such a joint distribution, the first term over here is my Monge-Kantorovich problem. This is the expectation under gamma of y minus x norm squared. Now you fix a positive epsilon and you add epsilon times entropy of gamma, and now you may take the infimum over all such gamma. Okay? What am I doing here? What I'm doing here is that when epsilon is 0, this becomes my Monge-Kantorovich problem. When epsilon is positive, what is the entropy of Brunner's solution? Well, Brunner's solution is supported on a graph, right? It's a very degenerate solution. Its entropy is infinity, and it's not in the domain of this problem. And so for every positive epsilon, the solution is not the Brunner solution. It will have some density. It will have a joint density. So for every positive epsilon, you have a joint density. But as epsilon goes to 0, you allow for densities which are piling up more and more towards the graph of the Brunner solution, but it is never the Brunner solution. And this is the idea of regularization. And so the picture over you see here is that this is, if you take there's a graph hiding here, which is my Brunner solution, which is the optimal transport map between these two one-dimensional densities. And as you increase your epsilon, this is a heat map of the joint density, it becomes more diffuse. By the way, can you guess what happens as epsilon goes towards infinity when you allow basically entropy to take over? What's the optimal solution? The product measure, mu and mu. It just, that's the maximum entropy that we can get from there. The optimal solution, the optimal coupling of this problem for every positive epsilon, this is called the Schrödinger bridge at temperature epsilon. I'll come to this reason why it's called the Schrödinger bridge, because indeed it was suggested by Schrödinger. Is this problem clear? Okay, so this is the problem of entropy regularized optimal transport. Its solution is called the Schrödinger bridge. Epsilon is like a tuning parameter, correct? Now, what do we know about the solution of this problem? Now, this is not a Brunner's map. This is a solution which is a joint density, but it is a very particular solution. The solution looks like this. There are a number of works from Forte, Ruschendorf, and Thomson, and etc. And also, I should mention Sizer's work. The Schrödinger bridge has a very particular solution. The joint density must look like the following type. What is the following type? It must be that this quadratic term must appear here. You would recognize this as the Brownian transition density, and that's important. It has a quadratic term here. There's the Gaussian term. The rest of the term cannot include any term that involves both x and y. It must involve terms which is only of x and terms only of y. And this is if and only if. If you can find such a joint density, which respects the two marginal density distributions. And here I have again messed up my notation. This is my mu, this is my nu. If you find such functions which respects my two marginal densities, it must be the Schrödinger bridge, and the Schrödinger bridge must look like this. So again, there is no gradient of convex function anymore. That's completely gone out of the picture because I must have joint density. But the joint density is very particular. It only has one term that depends on both x and y. And that term is a Gaussian transition density. The rest of the terms must be solely of x or solely of y. If you can find those terms, you are done. Good? Now, this is what statisticians actually estimate, and I'll come to this how. There's a wonderful, wonderful way to actually find this solution numerically. But when they actually find the joint density, they are not happy. Statisticians are never happy. Once you actually find the joint density, they again want to go back to the Monge map because that's what is attractive. If you pick up your grain of sand, you want to know exactly where you're going to transport it, not some joint density. You don't want to have additional randomness. And so what they do is that they do what is called a barycentric projection. They find out the conditional expectation under the Schrödinger bridge of y given x. And this term over here, as we will soon see, is a good approximation of the Monge map. And so this is a map which approximates the Monge map, which we get from the regularized problem. Good? How do I solve the Schrödinger bridge? By using what is called a synchron algorithm. is one of those fundamental algorithms that comes up all the time in many different areas of math. And this is one such application. So I've given an idea of what this single algorithm looks like. In statistics, in continuum, it is also called the iterative proportional fitting algorithm. By the way, I want to mention this wonderful proof by Forte in 1940s. It is not clear that this is a solution of the Schrödinger bridge problem, right? How does he actually prove this? He proves this by running the synchron algorithm by an iterative procedure and saying that the solution must be of this type. It's a beautiful proof. So here is what I'm going to run. Everything is on data, so everything is on discrete set. My mu and nu are uniform on 2-point sets, 0, 1 and 0, minus 1. Okay, half mass on these 2 points. I'm taking epsilon to be 1 for simplicity. And I want to find out my entropy regularized solution of entropy solution, which is my Schrödinger bridge for epsilon equals to 1. How do I do this? I'll start with the matrix that has only the Gaussian transitions. So what do I mean? Remember that the Gaussian transition looks like this, e to the power minus 1 over 2 epsilon y minus x norm square. So I'll fill in my matrix with this. So 0, 0 gives me e to the power minus 0 square over 2. That gives you 1. 1, 0 gives me e to the power minus 1 half. 0 minus 1 gives me e to the power minus 1 half and e to the power minus 2. So I fill in my matrix with my Gaussian transitions. This matrix does not have my correct marginals. So if I add these two guys, I don't get half-half row sum, and I don't get half-half column sums. This is what I'm looking for. How will I get this? Well, it's very easy. At the first step, I want to make my row sums half-half by dividing the row elements by the row sum and then multiplying by a half. So my row sum is 1 plus e to the power minus 1 half. I divide by 1 plus e to the power minus 1 half and multiply by half. So I get e to the power minus 1 half, 1 plus e to the power minus 1 half, 1 half. And when I do this, I get my row sums to be half-half. But now I've messed up my column sums. This is now 0.7 and 0.3. How do I do my column sums to be half-half? I'll do the same thing. I'll now divide the columns by my column sums, multiply by half. And now my column sums will become half-half, but my row sums are not. And so alternately, I will do both of these. I'll make row sums half-half, column sums half-half. And at the end of it, we hope, and this is true, I'll get a matrix which both matrices are half-half and half-half. And that's my solution of my Schrödinger bridge problem, because it takes a little bit of thinking that every such action only introduces elements which only depends on x or y, and never a term that involves both x and y. Okay? And this must converge. The single algorithm was suggested for solving optimal transport problem by Marco Couturi in 2013. It was an instant hit. I don't know how many thousands and thousands of citations he has in this paper. It was an instant hit. It just absolutely took over machine learning, so much so that in machine learning, if you talk to people about optimal transport, they usually talk about entropy-regularized optimal transport, and they don't even know what optimal transport is sometimes. There's a very good reason for this. Well, Marco Couturi shows that this is highly parallelizable. This computation can be done very fast. That's one. But there are other reasons for this. If you want to solve your optimal transport problem on finite data, going back to what Kantorovich was doing, you will solve your linear programming. Linear programming is a very well understood object. It will show you that you take about, if you have n data points, it will take you n cube many data things. And this OTL actually has bad dependence on dimension. On the other hand, it was shown by Altshuler and al. That if you use entropy-regularized optimal transport, you can cut down a dimension by n squared. Huge improvement when your n, the number of data is like, I don't know, hundreds of thousands. Huge improvement. So that's one reason why you would want to do this. There are other reasons, I'll come very soon. But once this was discovered, there's been absolute blossoming of applications of optimal transport in many different models. I don't want to get into each one of these, but this is an image that I've taken from J.C. Hutter's talk that like Wasserstein generative adversarial networks, trajectorial inference, many different areas now use optimal transport. But when they use optimal transport, they're always using entropy-regularized optimal transport, and they're always using synchron algorithm to solve it. I want to skip this slide, so let's go over this. Let's go to here. Good. So now I have something. I am interested in optimal transport for its geometric properties. I can solve optimal transport with entropy regularization because it is nicer for computation and for statistics. But do these problems actually, I mean, if I take my epsilon, my tuning parameter, to 0, do I recover my original problem that I'm actually interested in? This is a natural question. And this is where probability comes into play, right? You want to show that the sequence of regularized problem converges to the problem that you're actually interested in. There are a number of results that is known in this regard in the last, everything almost in the last 10 years. So this is my entropy regularized problem. As I take epsilon going down to 0, do I recover the problem at epsilon equal to 0, which is my W2 square, my Wasserstein 2 square problem. So back in 2012, even in 2004, it was shown that yes, this is the case. You actually recover the actual cost of transport by solving this and then taking epsilon going to 0. The proof uses large deviations. You also can show that the optimal solution that you get from here, this is the Schrödinger bridge, converges to my Monge solution. It is the one that is given by Brinier's thing, right? So as epsilon goes to 0, you actually converge here. You can also find this rates of convergence is a result that often gets used in statistics, which is that the rate of convergence of this two difference over epsilon is just the sum of entropies of these two marginals, entropy of mu plus entropy of mu. So we know, actually we know even the higher order terms. I want to say one single slide of why Schrödinger bridges are called Schrödinger bridges. And the reason is that it comes from a thought experiment of Schrödinger in 1931 to 32. And the thought experiment goes like this. Imagine you have gas molecules trapped in a very cold room. So this is a room which has been made very cold. This room is not particularly cold. Here, this is close to absolute 0. Now imagine you have gas molecules where at time 0, the configuration of these molecules is mu. So at time 0, these molecules are all huddled together in one corner of the room. As you know, the temperature is also talking about the frequency of these molecules, right? So if the temperature is very cold, then these molecules are not going to move very much. So if you observe the same gas molecules at time t equals to 1, you would expect that they have moved very slightly, but essentially the configuration has not changed. It's still about mu. Once in a blue moon, you would see something strange happen. What happens if at time t equals to 1, you see that the gas molecules had changed time to this configuration at the other end of the corner of this box. This is very unlikely to happen, but this is possible. You may have to wait for a very long time, but sometime or the other this will happen. The question that to ask here is that which molecule will go to which molecule and what path will they take? Is the question clear? So it's a physics experiment, molecules in a very, very cold room. You observe some configuration at time 0. You observe a different configuration at time 1. The question is which molecule goes to which molecule and what is the intermediate path that they take? The answer to this beautiful problem is for epsilon equals to any positive epsilon, what you get is that this is the Schrödinger bridge, which means that the joint distribution of this molecule position here and that position there is actually given by the solution of this entropy regularized optimal transport problem. It is non-trivial, but it is true. So that's one. What is the intermediate path that these molecules will take? Well, they will follow Brownian bridge, which diffusion epsilon. If you don't know what Brownian bridge, they are actually Brownian motion with the two endpoints pinned down. So it says something amazing about Brownian motion, as usual. As epsilon goes to 0, if you have mu and nu, your Brownian motion is automatically doing your Brunier map, is automatically doing an optimal transport optimization, where it's telling you if I have a molecule at x, where is it going to end up at time 1 is the one that is given by my gradient of phi of x where phi is the one that is coming from Brunier's solution. This is for epsilon going to 0, and that's because Schrödinger bridges converges to the Monge map as epsilon goes to 0. Okay. Running motion, of course, doesn't know optimization, but it is still doing this. Is it clear? So that's a physics intuition here. A little bit about statistical issues here. This is a very big field by now, so I'm really leaving out a lot of literature, but just some ideas about why it is popular in statistics. One of the reasons why statisticians like it is that entropy-regularized optimal transport does not suffer from curse of dimensionality up to a point. And here is where you see it. Suppose you want to find out mu and nu, you want to estimate the Wasserstein 2 square distance between mu and nu. How will you do it? Well, you take IID samples from mu, IID samples from nu, do your actual matching problem between mu n and nu n, and you try to figure out what is W2 distance between the empirical distributions, right? That's what you would do. Does this converge to the actual solution? The answer is yes, it converges. But as Fournier and Guillain show, and that the convergence is painfully slow, is n to the power minus 2 over d, where d is the dimension of the data. So now imagine that you have a 30-dimensional data. Is basically saying that it's order of n to the power minus 1 over 15, which is really, I mean, not good at all, to say the least. I want to mention also work by Horowitz and Karandikar, who also did some preliminary work on this way back in 1994. Mena and John Niles Speed show the sub-Gaussian. If we do the same problem, but now for entropy regularized, then you recover the parametric rate of n to the power minus 1/2 for any dimension. Amazing, right? It does not suffer from the curse of dimensionality except at one place. This order hides a constant, and that constant actually depends on dimension badly. But if you ignore that part, the complexity actually, I mean, there is no free lunch. Somewhere you have to pay the price. But if you ignore that, then the rest of it is parametric, is n to the power minus 1/2. These objects, if you want to do W2, if you want to estimate W2 between empirical distributions from here, the second thing our statistician would ask after consistency is that, is there a central limit theorem? Can I give confidence intervals? The situation is worse than bad. Not only there is no confidence interval, there is central limit theorem here, but the bias is bigger than the variance. It's just terrible. On the other hand, there's nice central limit theorems known for the entropy regularized problems. So for every positive epsilon, you have no curse of dimensionality up to a point. For every positive epsilon, from your data, you can get nice central limit theorem. You can find out what is your confidence interval. None of these things are true when epsilon equal to 0. And as we have shown, for small enough epsilon, you are getting approximately the right thing. That's what everybody, everybody. In fact, it's worse. Everybody would assume that things are compactly supported. No, I mean, sub-Gaussian is a very, very standard assumption in statistics. I mean, really, sub-Gaussians, well, okay, I mean, somewhere you have to draw a balance between what is reasonable to think and what is you can actually do. So there are things where it fails. There are certainly things, very prominent examples, even from neural networks, where things are heavy-tailed. They're not sub-Gaussian. But for, yes, I don't know, for, I don't think venture capitalists care about sub-Gaussian or not sub-Gaussian. They care about whether you can fool enough people and make money. Okay, anyway, so what we have learned so far is that optimal transport is very good because it's geometrically rigid. It gives a beautiful geometry underlying. It's bad because it's non-robust. Do something with your data and it does not converge to very nicely to your population. Entropy regularization solves this problem because it reduces the geometric, you do a trade. You trade your geometric property, you get a joint density. What you gain is robustness and your natural statistical properties out of this. There are many, many other beautiful properties of this, but we cannot quite get into, I mean, again, there's a There is a recent book by Philippe Rigollet, Sinochewi, and John Niles-Sweet called Statistical Optimal Transport. I'll take it as I'll promote this book because it's the first optimal transport book which is on statistics probability. And so I invite you to go and look into that book for many other applications. Okay, I want to talk a little bit about some of my own work here, my recent work on iterated Schrödinger bridge approximations to Wasserstein gradient flows. And the problem comes from something that is very popular these days called transformers. I'm not an expert on transformers. I suspect some of you might be. So what is a transformer? I'll just understand. Okay. This is with my collaborator, Zaid Ashawi, who is a machine learning and statistician, my colleague in statistics, and our students, Medha Agarwal and Garrett Malkahi. So I have learned all these things from Zaid here. So transformers are this neural network architecture which gets used these days in all these LLMs and those things. They were originally proposed by Vaswani et al. And the way to understand these transformers, these are pictures I've taken from these papers, Vaswani et al., Sander et al., and Geshkovsky et al. The way that you should think of transformers is that it's some kind of dynamical system on the space of measures. How does measures come into here? Well, there are tokens. There are some things called tokens, which are discrete points. If you pull these discrete points, there is some mean field interactions going on between these discrete points. If you pull these discrete points, you get an empirical distribution. If you forget about the fact that these are empirical distributions that are discretely supported and lift everything to the space of probability measures in general, then what you get is some kind of dynamical system on the sequence of probability measure. You have a probability measure, you push forward to another probability measure, you push forward to another probability measure, and on you go. Okay? How do you push forward this? In a very particular way, and this is where my model comes into play. So I'm going to talk about a dynamical system, which will look very, very strange at first, and all I want from you is just follow along, okay? So here's a dynamical system on measures. Start with the density rho naught, fix an epsilon, and consider the Schrödinger bridge gamma epsilon rho naught to rho naught. So I'm looking into transporting my density rho naught to itself. Unfortunately, no. Only if rho naught is Gaussian. If it is not Gaussian, we don't know it's going to be closed form solution. You would think, but no. So I have my rho naught, and I want to transport to rho naught. What do you think is the Brunier solution? Like, what do you think is the Monge map that is the optimal solution going from rho naught to rho naught? Just identity, right? If I take sample my x from rho naught, I would take x to x, and this will give me a cost 0. For every positive epsilon, however, I have a joint density. And this joint density is my gamma epsilon rho naught to rho naught. But in general, we have no idea what these joint densities. However, there's something that we can tell. We know that this must converge to identity. And so if I look into what is this barycentric projection, if I look into this conditional expectation of y given x equals to x, I know that this must be close to x. Not exactly x, perhaps, but close to x. Clear? So we compute this object. I look into this barycentric projection, which is given an x. I look into what is my conditional expectation of y given x equals to x, and I know this is close to x. And I do something very strange, and this really comes from neural networks, the transformers. If I sample x naught from rho naught, I look into twice x naught minus this barycentric projection applied to x naught, and that becomes my new random variable called x1, and I call its law to be rho 1. Very, very strange. But look at what I'm doing here. This is my twice identity minus the barycenter. As I said, my barycenter for same marginal is approximately my identity. So this is really approximately twice x naught minus x naught. which is just x naught. So really, rho 1 should be just rho naught, but not exactly, because epsilon is there, and a tiny bit changes my things. If you want to think in this kind of object, my molecules are just vibrating just a tiny bit. I want to know where is conditional expectation given where I am at x. Is this clear? Sorry? Oh, this is exactly what I mean. This is a push forward. This is exactly what I mean. But this thing actually creates a dynamical system on the set of measures. You can plug in any measure. You can compute the barycentric projection with the measure as the two marginals. You can calculate this twice identity minus this barycentric projection. And then you go to the next measure that comes out of its law. This is, oh yes, thank you. This is hash rho naught. Thank you. It's correct. I'll come to this. You don't even know where I'm going. So what do you mean by correct thing to do? I could be like doing arbitrary things here. So now that I have a dynamical system, what do? Let's iterate. So for every k, I have rho k, and I'm going to compute my Schrödinger bridge at epsilon with rho k as the same marginal, rho k and rho k. I'm computing my barycentric projection, which is approximately my identity. And I look into twice identity minus the barycentric projection. This is again approximately the identity. Okay, will you guys stop? So if xk is rho k, then I'm looking into the law of twice xk minus barycentric projection vk of xk, and that's my xk plus 1. Good, I do this. So for every epsilon, I get a sequence of measures, rho naught, rho 1, rho 2, rho 3, and so on. My question is that where is the sequence converging as a sequence? So what do I mean by this? I scale my iterations by epsilon. So I have rho naught, rho 1, rho 2, rho 3, and so on. I scale them by, I take continuous time. So I divide my time in intervals of epsilon, and I take my measures and I do this. So in neural, if you want to think in terms of neural network, I have a network, a transformer network, which has infinite depth. And so I'm kind of taking a scaling limit. At every iteration is my one layer of my transformer. And in my infinite depth, I get a continuous time. And so I'm looking into this rho epsilon. This is the floor of T over epsilon. So I'm making my time continuous. And I'm asking, what am I observing? So this is what I've simulated using particles. I'm starting my rho naught is my bimodal distributed density. And at every step, I'm computing this object, twice identity minus the barycenter, push forwarding my current rho. What do you think is happening to the sequence of pictures? Yeah, but a very particular thing is happening. Very good. It's actually becoming close to being normal. It's actually what you're observing is the heat flow. So this is a theorem that I want to talk about, that if you look into this, and if you look at this convergence as epsilon goes to 0, so epsilon goes to 0, you're packing more and more of this object in a finite amount of time. What it is converging to is a solution of the heat flow. Very surprising, right? It is from this iteration coming here. It was originally observed in this beautiful paper by Sander, Abna, Blondel, and Perry, and they really were doing transformers. They had no interest in doing anything else, because I'll come to what their motivation was. Their proof seemed a lot lacking. And so in this paper, we make this idea rigorous that such a kind of dynamical system actually gives you solution of the heat equation. There is no Brownian motion here, by the way. There is no random walk. It's a purely deterministic dynamical system on the space of measures, which is giving you heat flow. Okay, so here's a question I'll give the answer to. If instead of twice identity minus the barycenter, what happens if you just do the barycenter? Which seems more natural. Every time you compute the barycenter and you push forward, what do you think you'll get? Think about this. I'll give you the solution later. How much time do I have? So I'll try to stop in 5 minutes. Why is this happening? So I want to give a one-slide explanation of why this is happening. And the idea is this. As I said, if you take the same marginal rho, and if you compute my Schrödinger bridge, it is very close to my Monge map, right? But how close? Well, if I look into my barycentric projection, this is my identity. What is the next order term? It turns out that the next order term is actually epsilon over 2 times what is called the score function. This is the gradient of log of rho. That's the next order term. So it's identity plus epsilon over 2 gradient of log rho. And now you see some magic happening. Why twice identity minus the barycenter? Because if you compute this approximation, if you plug in here, what you get that what you're doing is x minus epsilon over 2 gradient of log rho. And now this discretization of this dynamics is telling you that your xk plus 1 is approximately xk minus epsilon over 2 gradient of log rho k of xk. This is an Euler iteration for the following ODE. Xt dot is minus gradient, well, there's a 1/2 gradient of log rho t, where rho t is the law of xt. But if you solve this ODE, you get the heat equation. This is the only solution for this. So what happens then? But it tells you what happens in all linear combinations. Exactly what you want to know. Okay, so again, why is this twice identity minus the barycenter is coming up? Well, the reason why it came up in the original paper, because that was the right thing to do for the transformers. The reason why this comes up here is because it gives this beautiful discretization, which when you properly scale time, it gives you the heat equation. Okay. Okay, I don't want to get into how you even get into this kind of approximation. You have to come up with a guess for what the Schrödinger bridge is. It has to do with large event diffusion. Won't skip this. Okay, so concluding remark here. So what was Sanders? What was this paper Sander, Abla, Blondel, and Perry doing in transformers, and how did they get into Schrödinger bridges? So if you know anything about transformers, you think that there is this in transformers. There is this attention matrix, and this attention matrix is a stochastic matrix, right? And your dynamical system moves by looking into this attention matrix and then moving forward. What they suggested is that, okay, what happens if we don't take stochastic matrix, but take doubly stochastic matrix? But if you take doubly stochastic matrix, and if you look into how the tokens are progressing between layers, it's exactly this dynamical system that pops up, except over particles, not really over measures, but over particles. And they work this out. And then they say, okay, forget about particles. We can't do really about particles. I have this measure. Let's write down what the evolution of these tokens are going to be. And then they say, okay, this must be the heat equation. They don't give a rigorous proof, but that's exactly how they do it. And what it is showing is that these tokens, as they're evolving in a trained transformers, these tokens, as they're evolving over the layers of the network, is converging to the heat equation. If you want to prove, so we only prove one part of their paper, which is the continuum part. But as I said, their paper actually is discrete over particle systems. So we're doing a very complicated mean field evolution. If you want to prove that part of the paper, you have to prove that there is some consistency of the estimation of score function, which we don't know yet. We don't know how to prove such a thing. All right, so this is the challenge I asked. What happens if you do instead of twice identity minus barycenter, what happens if you do barycenter and if you do this? Anybody wants to have a guess? So remember the sign flips, right? Sign will flip twice identity. But we don't know exactly. We can actually find out computations, and we can do it we can do some explicit computations over Gaussians. We can run simulations. It runs the backward heat equation because the velocity flips its sign, and you just run your process backwards in time. And so this is pretty interesting way of generating a backward heat flow by looking into this Schrödinger bridges and running a dynamical system. In the paper, we also do other kinds of diffusions, and Wasserstein gradient flows forward and backward as well. But the proofs can only be done in the forward directions. The backward, as you know, is pretty ill-posed, and we don't have yet proofs for that. But they seem to work. All right, okay, I'll stop here. So thank you very much for your attention. Yeah. No, you don't get the exact transportation. You only get an approximation. And so you only get the approximation for every positive epsilon. You only get an approximation. And then there are theorems which would say that as epsilon goes to 0, your barycentric map will converge to the actual transportation maps. But you are not exactly computing the actual transportation map. Yeah, so that's, well, if something is NP hard, then of course it will remain NP hard all the time. So you can't. Right. So exactly. So one of the things that I would like to encourage here is that the reason that optimal transport, if you want to do it, is very hard because it's solving a very hard linear programming problem. But this entropy regularization makes your life very easy. This is a particular regularization. There are other regularizations people use. They're not this nice. But this particular regularization, for whatever reason, well, we know whatever reason, there's some physics behind it. It makes your life very, very easy. So maybe if you take your favorite optimization problem and plug in some kind of entropy regularization, you might expect to get a good answer from here. The reason why entropy regularization, I mean, I say there are many reasons why there's the physics here. But one thing I did not say here is that once you introduce that positive epsilon, it becomes a projection in Kullback-Leibler. In the Kullback-Leibler sense, and those are nice typically. There is a very, very interesting and deep connection between Kullback-Leibler and optimal transport, which you only see when you actually do the proofs. Right, good question. So how do you actually choose epsilon? Well, so this is, of course, so, well, I once talked to John Nansweet, and this is John would say that people typically would like scale epsilon with the data size n. So they would take some constant of 1 over log n or something like this and slowly decrease it. But exactly how they do it, well, the problem is that only, I mean, this is a very active field. So every year we are only learning better and better estimates of things. So now we have some idea of how epsilon, I mean, for every epsilon you get some error. And we have now much better ideas of what is this order of this error depending on the function of epsilon, n, and d. And then you can try to come up with some optimal way to do this nowadays. But we are still far from understanding all these convergences. So there are lots of, I mean, it might seem like we know everything, but no, no, no. This problem is actually, area has lots and lots of open problems. We're only still only scratching the surface. Thank you.